So, in the introduction, in the last video, we have seen how semiconductors are better than vacuum tubes. As a part of the introduction itself, let us now look at how semiconductors differ or compare with other types of materials like conductors and insulators. Metals, which are said to be conductors, they possess very high conductivity or low resistivity. And here rho is resistivity, sigma is conductivity. And as you can see, the typical scale used for mentioning the conductivities or resistivities, these things, that scale is logarithmic scale. And therefore, we shall be careful about it. And also one more important thing we need to note is that the resistivities or conductivities, if you see, there is a bit of overlap. So if you see resistivity, metals have very low resistivity in the order of 10 to the power of minus 2 to 10 to the power of minus 8, which is quite low resistivity, while semiconductors have in the order of 10 power minus 6 to 10 power 6. So 10 power minus 2 to 10 power minus 5, that range, it is metals as well as semiconductors. So there is a bit of overlap. So there are other properties that will determine whether those materials are treated as either conductors or semiconductors. So you don't have to worry much about this overlap. Okay. Now, similarly, insulators have very high resistivity, and there is no overlap between semiconductors and insulators, luckily for us. So let me once browse through this entire slide. So you have conductors which have very low resistivity, then semiconductors which have the mid-range resistivity, and insulators which have very high resistivity. Whereas if you talk in terms of conductivity, metals have very high conductivity, semiconductors have mid-range conductivity, and insulators have extremely low conductivity. And of course, these numbers which are given in the NCERT textbook, they are different, based on the reference that you choose. So in the internet, you may see different numbers. Students don't need to worry. Just stick to the NCERT numbers and you will be through. Okay. And more importantly, in the examination, in the final examination also, they will give you numbers which you are comfortable with. They don't confuse you. So you don't have to worry. Fine. Now, the question is, how come metals have such high conductivity or low resistivity? And semiconductors, why there is a mid-range, why they are in the mid-range, and why insulators have such low conductivity or such high resistivity? So this is the issue we are going to address. And for that, we need to briefly enter into the solid state physics. Okay. And it's not so difficult. It's easy only. Now, let's say in any material that you have, large number of atoms combine to form that particular material, a plate or a spherical ball, whatever you see as an object. So it is made up of large number of atoms. Now, according to the solid state theory, suppose if you have any tetravalent atom like silicon, germanium, whatever you take, in its outermost shell, as you know, there are 4 electrons. Silicon has 4 electrons in the outermost shell. Okay. Now, when you have only a silicon atom or n silicon atoms are independent of each other. That means they are not a part of any material or any plate or anything. Each atom is an isolated entity. Then in each silicon atom, in its outermost shell, the 2 electrons will be in the s orbital, and the p orbitals will have the remaining 2 electrons, whereas 4 places within the p orbitals will be empty. As you know, in any shell within an atom, you have s orbital which can contain 2 electrons, and p orbitals, you have p1, p2, p3. In total, it can contain 6 electrons. Silicon has 4 outermost electrons, of which 2 will place themselves in the s orbital, and the other 2 will be in the p orbital. Okay. Now, when silicon atoms are isolated, then each silicon atom will have 2 electrons in the s orbital, and 2 electrons in the p orbital, right? So you have n silicon atoms. So 2n number of electrons, when you look at all of them together, 2n electrons are in the s orbitals. That means that energy level. And p orbital, the higher energy level, will contain 2 electrons in each silicon atom. So 2n electrons will be in the higher energy level, 2n electrons will be in the lower energy level when all silicon atoms are isolated from each other. Now that is the rightmost side of this picture. Now, as you go towards left in our picture on the board, okay, it's like the atoms are coming closer to form a substance, or like a plate or a material. Okay, so as the atoms come close, what will happen? So as you know, there will be some interactions amongst the atoms, and therefore the outer electrons, the 4 outer electrons, they form covalent bonds with each other. Particularly these 4th group elements, they have catenation. Accordingly, they form long chains through these covalent bonds. And therefore, what we can say is that as the n silicon atoms are coming close, it is like each of them have 4 electrons. So 4n, that the electrons in the outermost shells of all these 4n electrons, they are now being influenced by all the silicon atom. That means all the n nuclei start influencing these 4n outermost electrons. And therefore, instead of having an s orbital and a p orbital, okay, in each silicon atom, the outer orbitals, since they are influenced by the other nuclei as well, now they are molecular orbitals, and therefore the energy levels start changing. So between, in the s itself, there are 2 energy levels. Those energy levels start widening. Okay, similarly the p orbitals also, the 6p energy levels also start widening, and there will be some mix. Okay, so the energy levels completely change. And accordingly, because it is a n silicon atoms and all the nuclei are influencing all the 4n electrons, in total you have it is like this. The outer electrons can be anywhere, okay, because they are under the influence of all n nuclei. So now, as you know, s orbital has 2 energy states, p orbital has 6 energy states. The total number of energy states in each silicon atom is 8. There are n such silicon atoms, all of them are now together. So 8n energy states which are influenced by n nuclei will be formed. And accordingly what happens is as the gap between silicon atoms keeps getting, keeps reducing, so there will be a region C, that is where typically your metals fall, wherein you have continuous energy states. That means the energy gap between consequent states is so low that electron may, thermally jump above and then again de-excite like that. It's very easy. So the conductors fall in the region C. The interatomic spacing in the conductors is around the region C, and therefore what happens is the electrons seamlessly move. Okay, so they have foreign, there are foreign electrons and 8 n states, and electrons seamlessly move from one to another. Higher energy states are typically called conduction band, and low energy states, which means that you are more strongly held by the nuclei, they are called valence bands. Okay, and therefore what happens is that as the as in the metals, the conduction band and valence band, that means the higher energy states and lower energy states. So the foreign states which are on the higher side, you can call them as conduction band. The foreign states which are on the lower side, you can call them as valence bands. And since they are continuous, there is no gap, and therefore electrons can easily go from valence band to conduction band and so on. And therefore, in metals, the electrons seamlessly go from valence band to conduction band. Whereas if the distance further decreases, because as you go towards left, it's like the distance decreases. So what happens is an energy gap is created. Okay. So this energy gap, what it will do is it will separate the conduction band, that means the upper foreign states, from the lower foreign states. So the lower foreign states form the valence band, upper foreign states form the conduction band, and they are separated by an energy gap. Now, if the energy gap is low, they are semiconductors. If the energy gap is very high, then they are insulators. So that's what we have from the solid state physics and all. You don't have to worry too much about this. Never a question which is very deep based on this has been asked. So students don't need to worry. Roughly what you need to understand is, as these elements come close to each other to form a material, instead of each element having some energy states in its shell, the outer energy states are commonly owned. Now, based on the atomic spacing, either the 8 energy states will be continuous, almost. Continuous doesn't mean there is no quantization here and all. There is quantization. So you have a continuous states, okay, which are very close to each other, almost like they're so close that you can call it as continuous. Accordingly, electrons can seamlessly move up and down based on some thermal agitations, etc. Whereas when the atomic spacing becomes even tighter, as it gets tighter, what happens is the upper foreign states and lower foreign states, in between them there will be an energy gap, and as the energy gap increases, it will become very difficult for the electrons to jump from the valence band to conduction band. That is the idea you should get from this slide. Okay, now, so what happens in conductors? Because of the overlap, electrons can seamlessly go from valence band to conduction band, and conduction band electrons conduct electricity. That's why they are very good conductors of electricity. Now, in semiconductors, the energy gap is relatively small. So what happens is, in semiconductors, as you heat up the semiconductor, due to thermal agitations, the electrons can jump from valence band to conduction band. So they do have some conductivity. Whereas in insulators, the gap is much larger than 3 electron volts, and accordingly, they typically don't have many electrons in the conduction band, and therefore they do not conduct electricity. Okay, so this is a very simple idea that you need to have about the comparison between semiconductors, conductors, and insulators. Thank you.